My goal of this talk is to try to fuel your imagination by showing you some of the ways that I've been exploring software as computational media. Modern software is not very soft at all, and it's a bit ironic that it's even called software. We use purpose-built applications with little room for appropriating them beyond what the designers intended them for, and very few of us actually modify our software. We've come to take the concept of applications for granted. We use one-size-fits-all applications that are difficult to adapt, so we have to adapt. They are incompatible with each other, so we have to compromise when collaborating with people who've made other choices in tools than we have ourselves. Applications are also rooted in a tradition that strongly separates developing and using software. There's developers and there's users. Users don't change their software, they just conform. Let me take you through a small scenario to illustrate this point. Say hello to Elise. Elise is an experienced grant writing consultant currently working on a large EU grant proposal for urban renewal in a European city. So she's a very typical modern knowledge worker. Elise uses a cloud-based word processor that her agency has a license for that supports real-time collaboration, so it's easy for her to work on the text with the various stakeholders in the proposal. Elise uses a bunch of extensions that can help her adhere to the different proposal templates. For this particular one, she uses one that makes sure that the correct sections are there and also that the sections doesn't exceed the max word count. The regulations this year has slightly changed and the maximum word counts has decreased for some of the sections, but this particular extension hasn't been updated and the author is not responding to email. Elise knows that it has to be a simple change and the extension is open source, so she even thinks that she's found the place where the code needs to be changed. But she knows that she can't update the extension in the word processor marketplace as she's not the author. Perhaps she could deploy her own version, but she has no idea of how to do so. And also she doesn't know whether she's even allowed to publish a new version of somebody else's extension. Her company does not want to spend money on an expensive programmer to help Elise, so she just decided to keep a note of the new word counts and handle them manually. It's just a couple of sections anyways. A couple of days later, Elise succeeds in recruiting a large progressive environmental nonprofit organization as a collaborator on her grant. She sends an invite to the shared grant proposal, but later she gets a message back that the organization won't use proprietary closed source software and also that Elise's word processor is incompatible with the extensions that they use. Now Elise managed to export the documents to a format that she can share with them, but the edit history and comments made in the document are gone from this version. The other collaborators insist on using the cloud editor, so Elise now manually keeps track of merging changes and managing conflicts in the text. A morning sometime later, Elise opens the word processor and all the traces of the extension is gone. The menu bar displays a small red notification. She clicks on it and is greeted with extension culture proposal has been disabled due to version incompatibility. A new update has broken the plugin. Elise sighs deeply and returns to counting words and managing sections by hand and seriously reconsiders her life choices. Here, Elise's personal digital sovereignty is violated. She cannot independently make changes to her software. She has limited control over the data that's trapped in her applications, and her autonomy is restricted by automatic software updates that are imposed upon her. In my work, I'm interested in understanding the mechanisms that enable and prevent the development of what I refer to as personal digital sovereignty and how this notion is a prerequisite for the development of digital literacy at large. In this talk, what I'll do is I'll talk about how software could be made different to support personal digital sovereignty. To do this, we need to redo how we conceptualize and build software. Instead of creating applications, we should create computational media that allows users to collectively piece together their own personal computing environments. Boxer here is a system developed at MIT in the 80s by Andy DeSessa and Hal Abelson, and it demonstrated the idea and power of thinking software as computational media rather than monolithic applications. In Boxer, development and use happen in the same medium, and tools and data could elegantly be combined across different domains of work. This figure to the right is from Andy DeSessa's book, Changing Minds, and illustrates the difference between monolithic non-modifiable applications and computational media. According to DeSessa, applications may have gaps and overlaps, as you see to the left of the figure, but a computational medium can be seeded with small extendable tools that can be organically enriched, altered, and combined, as it says here in the figure caption. Now, DeSessa was not the first to talk about software as a medium. Almost 50 years ago, Alan Kay famously imagined future computers taking the form of paper pad-sized devices he called Dynabooks. Interaction would, according to Kay, happen through personal dynamic media that would let us mold and channel the power of the computer to our own needs. In Kay's vision, two kids, Jimmy and Beth, were sitting in the grass and playing Space War across their linked Dynabooks. They find the game a bit too easy, so they start to collaboratively tinker with the program code to change the gravity on the ship to make the game a bit more challenging. So in Kay's vision, software was an expressive, creative medium, something that could be tinkered with and appropriated for personal and idiosyncratic needs and desires. There weren't as such the modern distinction between applications and documents, or between developers and users of software. So now, this was 50 years ago. How should a modern computational media be like? I believe that it should have these 6 qualities. It should be malleable, shareable, distributable, interoperable, composable, and computable. That was a bit of a mouthful. I'll just take them one by one. So malleable software lets users appropriate and repurpose their tools and documents in personal and idiosyncratic ways. Software should be both reprogrammable to those that has the skills, but also reconstructible from ready-made parts. Shareable software allows users to seamlessly collaborate both synchronously and asynchronously on any kind of data and any kind of program. Distributable software allows tools, documents, and data and computation to span and move easily across different devices, platforms, and servers. Composable software allows users to combine tools and functionality beyond traditional application boundaries and incrementally add functionality to tools as needed. Interoperable software allows users to collaborate on shared data using their own tools. And finally, software should be computable. It should be possible to do computations with what you see on the screen, which doesn't seem too much to ask when what we are using are called computers, but it surprisingly is. Also, all of this should be possible in a live medium. So isn't the web a computational medium? In fact, web pages are quite computational. You can mix traditional media with computation, and everything on a page, the content of the document object model or the DOM, can be addressed by JavaScript. And there's a console directly available in the browser. So I can jump in and, for instance, do something like this, run a bit of code that makes this header animate. Let's stop that again. Web pages are easy to share a link to, and they're easy to access on different devices. Some web pages even support real-time collaboration like Google Docs or Figma, and some pages are editable by everyone like on Wikipedia. But in traditional web, the document is ephemeral, and local changes you do, like I just did, don't persist or are seen by other users of the same web page. But what if we made a little change so edits were saved and sent to other users? I made this system called Webstrates, and that's basically what it does. In Webstrates, changes to a page called a Webstrate are stored on a server and synchronized to other clients of the same page. So here I just use the developer tools to edit the DOM of a page. And now on the other web browser, I will add an attribute to the body that makes the whole body editable. And here I have a $1 implementation of Google Docs-like editor. So changes to the DOM are synchronized. The principle in Webstrates turned out to scale quite well. We've been using it to build sophisticated collaborative software like this cross-device whiteboarding tool here. In fact, now Webstrates has been used in some capacity or the other in more than 25 research publications since we released it in 2015. Webstrates has some interesting qualities because it's possible to introduce a traditional application document-like relationship between two Webstrates using an old hypermedia principle called Transclusion. Transclusion means the inclusion of part or all of an electronic document into one or more other documents by reference. And you see it here. So to the right, we have an unstyled document Webstrate that is then transcluded into an editor Webstrate here that has various tools for marking up the text and refers the style sheet to give it the ACM style. What's quite neat with this is that synchronization of content happens through the document Webstrate, through the medium. So users can share a link to the document, but open it in two different editors that then can interoperate through the document. So imagine a scenario of Bob, a professor to the right, who prefers a WYSIWYG editor, while his grad student Alice prefers a single column light on dark editor. Bob, he can edit the abstract down here, and the changes will synchronize to Alice's editor as well. Now, Alice can use this mechanism to distribute work across multiple devices. For instance, to have a live print preview on her iPad while she works. A figure in a document can similarly be a transcluded Webstrate, pushing this idea a bit further. This enables editing the figure with different types of interoperable editors, while the figure live updates in the paper on the iPad. A bitmap-based editor on a tablet can be used for sketching, and a vector graphics-based editor on a laptop for making the final figure, while the whole thing updates in where it's referenced in the paper. What you see here is Alice's editor from before. And the editor is not only visually different from Bob's WYSIWYG editor, it's also functionally different because Alice has a tool for handling citations. So I can scroll down the text here and I'll write Weiser, mark the text and hit the cite button over here in the toolbar, and the reference is added to the text. And if I scroll down the bottom, you see that it's added to the list of reference as well. And this tool uses another Webstrate, a bibliography Webstrate or Bibstrate, as its database over papers. And I can open that. It's transcluded into this document, but hidden with CSS. But if I press here, I open it. And it's a small application where I can import BibTeX in a DOM-like format, and then I can refer to them with this ID from the tool on the other side. Let's close this again. You could imagine that Bob, he would be interested in having this tool as well. Imagine also that Bob is not super technically savvy, so he asks Alice to install the tool for him. The editors are built using composition through transclusion. So a tool is a Webstrate in itself and just referenced in the different editors. So what you see now is that Alice extracts a snippet of code from her editor, opens up Bob's editor on her machine, and adds the snippet of code to Bob's editor. And immediately there's new buttons in Bob's toolbar, and he can go in and write a keyword, hit the new cite button, and another reference is added to the text. So what you just saw was collaborative extension of a user interface through composition live during runtime. The editor, this is possible because the editor is also a Webstrate, and therefore it's malleable. And Alice can edit Bob's interface remotely while he's using it, just as how they are working on documents together. What is application and what is document here starts to depend a bit on use. We've been using the concept of information substrates, or just substrates for short, to denote this kind of software artifact. That's also where the name Webstrates comes from, short for web substrates. These substrates, they embody content, computation, and interaction, and they can act as application in one use situation and document or data in another, as you just saw with the bibliography Webstrate. So we call the software artifacts that make up computational media for substrates. With the Codestrates project, we've explored how this substrate idea could be pushed even further. Codestrates is an authoring environment for Webstrates that allows mixing traditional media with executable code, sort of like a Jupyter notebook, if you're familiar with that, but where it's also possible to create real-time collaborative software, like an interactive physics report like this one that can collect and analyze accelerometer data from a phone, and then have the students collaboratively process the data through programming in the notebook. Here, it's been used to create a simple multiplayer tank game that the students debug together while playing it. The bullets doesn't really bounce off the walls, so they break out and fix the line that's broken. As soon as it's fixed, they resume playing. Okay, so here I'm just going to show you the basics of Codestrates. I've opened a blank Codestrate here on my slide, and let's start by giving it a name. So we will call it Live 2021 demo. It works very much like a computational notebook. I'll add a section here. I'll call it the demo, and now I'll add a bit of content. Call this a body paragraph. I'll just write "Hello World," very original. Let me make this a header. I'll just go and edit the HTML here to make it an H1, save that one. And I don't want this styling, so let me remove this class. Okay, now I will try to lock this paragraph. And what I can do now is I can full screen this one, and then we have a small static web page that we've created. That's not super interesting yet. Let's add a bit of styling to this. I'll add a so-called style paragraph where I can write some CSS. Let me just give this an ID so I can refer to it. So this one, main, let's give it a background color, oops, white, and a color black. And let's give it a min height of 200 pixels. And I'll just give it a height of 100% that is in effect when it's full screened. Okay, now let's say that we have a class called inverted here, where the background color is black and the text color is orange. Now I can add this class to the body paragraph up here by writing inverted, and then we see it taken in effect. Now I want to create a small sophisticated piece of software where I click on this one up here to have it swap or toggle the inverted class. So let me add a bit of JavaScript. I'll just write completely plain JavaScript here. So I'll do document.query, select the main, add event listener. I'm gonna click and have an event handler function and just say that when you take the target, takes its class list and then toggle the inverted class. Oops. Okay, let's try to run this and we see it works. All right, now let's click the small running man here, which will mean that this code will run on page load. And then let's try to full screen this one. Now we have a full screen application. But what I'm just going to do now is I'll break out of this one here and open it in another browser view. And then you see that the application state also synchronizes here. Let me then try up here to break out again, and let's change this one to pink. Okay, so here we have use and reprogramming collaboratively. Let's close this one. One thing I want to show you with Codestrates as well is that it is, oops, let me just close this properly. It is reconstructible. So say that this was an example I was making for my students in class, and I wanted to turn this into a slideshow. Then Codestrates has a package manager where I can install some ready-made parts. In this case, I want to install a presentation package. So let's do that. I'll find the presentation package, install it. And you see immediately a couple of buttons is added up here. Now, I don't have any slides yet, but I can just turn this one into a slide and then hit the play on presentation. And now the presentation runs. Let's full screen this one again. Okay, let's turn these into slides as well. Let's click up here and then let's run. And then I have the code on my slide as well as the example. Okay. Final thing I want to show about Codestrates, which I find interesting with it, is that it's implemented in itself. So the implementation of a Codestrate is contained within the Codestrate. So from the sidebar out here, I can open the different sections that makes up the implementation. For instance, the bootstrapping of the whole thing, where, for instance, the Codestrate object is defined. So each notebook contains its own implementation, and for good and for ill, can be reprogrammed from within. Okay, we've used Codestrates to as a platform for exploring the effect of computational media in the wild in actual use. We collaborated with a nanoscience lab here at Aarhus University to study the potential of computational media in their work. The Anderson lab is our world leading in what's popularly called RNA origami. So they fold RNA to small mechanical contraptions with the goal of, for example, making small robots that can release drugs in the body on command. What we did was to observe them, and one of the things that we observed was that one of the big struggles were maintaining and sharing computational environments for doing simulations and doing analysis of data. So through participatory design, we built a prototype of a lab book as computational media. It aggregated some of the many scripts and tools they use in sort of a computational notebook, but where code wasn't front and center, but still accessible behind the scenes. The prototype addresses just a small part of the dry work they do, so their computer work. The wet work is when they actually go to the lab. So two takeaways on shareability and malleability I want to share with you from this study was that real-time collaboration wasn't really super important to them in day-to-day work, but it was critical when they needed help. Here they really loved the idea of just being able to share a URL to their whole computational environment for an experiment and invite a more capable peer in to help debug something. Sometimes this more capable peer would be at the other side of the Atlantic. Similarly, with reprogramming, it should be possible, but not something they did every day. So we departed from the traditional computational notebook style where the code is front and center to something where it can be dug out when it's needed. This prototype also shows how a lab book can be reimagined as something that breaks the boundaries between applications and documents, and also between the different activities they do of documenting research, running simulations, doing data processing, etc. All right, that was Codestrates. I'll also talk a bit about another project that we've built on top of Webstrates that's called Videostrates. Here we experimented with a computational media approach to video editing by reifying video compositions as substrates. A videostrate is a webstrate that represents a video composition, and the URL of this webstrate can then be sent to a service we've built that can render it to a video file or a live stream. So here we see a simple videostrate to the right where I showing the DOM, and the same videostrate being rendered in a videostrate player to a stream, sort of like a YouTube stream that you can run and skip back and forward in. Videostrates uses a simple declarative notation where video elements with the composited class here will be included in the video based on a given start and end time. What you see here is just a 15-second video consisting of 3 clips from the paper, the video that we submitted with the paper. So in the example in the previous slide, the videostrate was stored as a webstrate on the Webstrates server together with a webstrate representing the video player. The video player, when loading the videostrate, asks the video streamer to render it and then can control the playback over WebRTC. Any change happening to the videostrate down here while it's being played will live update even while the video is playing. That the video is a web page also means that we can use CSS to create, for instance, spatial compositions of clips, like here, the same clips just laid out spatially this time, but also use CSS animations that we sync to the timing of the video. Now I paste in a CSS animation here, and you will see that immediately the stream changes, and now the videos will wipe down instead of just appear. We can use the principle of transclusion again to create, for instance, a timeline-based video editor like the one here that's inspired by Apple iMovie that can transclude and edit a video straight through an iframe. So here it loads a particular video straight and lets the user edit it in a drag and drop fashion. So let's just get back to Alice and Bob and see this in action. So here, Alice and Bob are making a video mock-up of a UI they are working on. They record some clips on their phones, and then they open the link to the video straight they're working on their phone, which allows them to upload the videos. And you see the video clip appearing in the editor. Now they can collaboratively start to cut the video, and they can open a preview of the video on a large display that live updates as they cut the video. And what Bob he can do now is he will open a subtitle editor on his computer that points to the video straight and start adding subtitles. The timeline editor doesn't know about how to edit subtitles, but they still appear in the stream. Finally, they want to add some effects, but the timeline editor is a bit too primitive, so they just open up the developer tools in the browser and start editing the Webstrates directly to add an animation. So Webstrates allows working collaboratively with video in a similar manner as what you saw earlier with text. Interoperability is achieved by expressing video compositions using the DOM and then synchronizing the DOM through Webstrates. Webstrates also makes video compositions computable. So here we have Grace. She runs a small one-woman video production and effects company and wants to create a small opening logo for her videos. So Grace, she records a bit of video on a green screen, imports that video into a combined Webstrates and computational notebook that she's made that uses a shader to do chroma keying to replace the background with an image. She then renders this video to a file, and so she can download it and open it in another Webstrates notebook that she's been working on. Here in this notebook, she overlays the video as a texture in a 3D scene with WebGL. And while she tinkers with the animation, she can show the Webstrates in the video player to see a live preview of what she's doing. What you saw here was that a complex web page, such as a computational notebook expressed as a Codestrates, can be rendered as a Webstrates if it just contains elements that the Webstrates server understands. To programmatically manipulate and generate video, we're using custom elements that Webstrates introduces that allows us, for instance, to draw on a canvas every time the time of a Webstrates updates. The point I want to get across here is that moving general functionality such as rendering and synchronization and playback control down into the medium allows a new level of computability and interoperability and also freedom in tool choice when, for example, in this case with Webstrates, working on video productions. Okay, I want to get back to Codestrates a bit because we have recently been developing Codestrates V2, which is our attempt to move the principles of our first Codestrates principle further down into the medium. Our experience with using and having others use Codestrates in particular taught us that it was a bit of a straitjacket to be forced to work in the notebook format all the time. Also, that the unconventional interface to programming alienated some people from trying out our platform. So together with our second iteration of Codestrates, we also built some more conventional authoring tools for Webstrates, built this authoring environment called Cauldron. I can open it here. It looks very much like a regular IDE, and I can just try to find the slide that I'm on here. Let's see, it's called Codestrates V2. Here it is. And in many ways, you can say that this one is a more pragmatic approach. Okay, and this IDE lives in the web page. I can detach it and dock it and stuff like that, but now I'll put it away for now. So Codestrates V2 is a code execution and code editing framework for Webstrates. It introduces the concept of code fragments that are reified executable code that can be edited through editors, and these editors can be instantiated anywhere in the user interface. Cauldron, as you saw before, is a conventional looking IDE built using the Codestrates framework and loaded into a Webstrates using the Webstrates package manager, which again is a generalization of the package management mechanism of the original Codestrates as an independent framework for Webstrates. While our first version of Codestrates was a computational notebook, this Codestrates V2 allows us to is a foundation to build computational media, like, for instance, a notebook. This you see here is a simple JavaScript-based Jupyter notebook clone called Ganymede that's implemented on top of the new Codestrates V2 framework in around 200 lines of JavaScript. And you can see I can run the cells here. There's a bit of interactivity here. There's some data that's visualized using Vega Lite that we import up there. And I can make a small change so you see it update. And these are markdown cells that I can double click and edit. Let us open Cauldron for this one. And here you see the implementation. Now it is, I counted yesterday, it is 200 lines of code if you strip all the comments. And what Codestrates V2 provides is a an API for easily instantiating these different fragments. Those are the fragments that are in the notebook, and instantiating editors for editing them. And in fact, these are just the same editors as we have in Cauldron. So if I double click on this one, you see these two are basically the same stuff. And if I edit it over here, it will also be reflected over there. Okay. The last thing I want to talk about is programming in computational media. Through our work with both Codestrates V1 and V2, we have struggled with making interactive software truly reprogrammable. We found that it's easy to make JavaScript editable, but it's hard to make it accessible to anyone except for the authors to actually edit it. Also, we found that the JavaScript programming model with its eventlessness and such lends itself relatively poorly to live collaborative programming. And when building interactive software, it easily results in complex code. In our most recent work, we've experimented with a programming model that we believe is better suited for programming computational media. Our idea is to express interactive software as a declarative data structure. I'll show you what I mean by that in a second. This is still work in progress. We currently have a paper on some of these ideas under review with my collaborators here. Primarily, Marcel and Luke have been the driving force in this work. But I'm going to give you a sneak peek, and then hopefully sometime soon, when a paper gets accepted, I can flesh out all the details and also reveal to you the name of the project. Here's a small unfinished program in our new programming model. And what I'm going to try is to finish it up. So I want here to build a small clickable counter. It will show up here that counts how many times I've clicked on it. And in the top here, we have something we call the concept definition. And I've defined a counter concept that has some schema saying that it has a count that's a number. Beneath here, I have a template that can render a concept to the UI. And I already have some pre-baked, for instance, a div here that refers the concept counter. And let's fill a bit more in so it actually shows a count. So let's add a span here. I'll just add something for later, and then I'll explain what that is. Go. You have clicked this text and then refer count. There we go. Times. Okay. So now it says that I've clicked it 0 times, but obviously nothing happens yet. So let's try to make it interactive by adding an action to the counter. Actions describe valid transformations to a concept's state. So let's try to add that. I'll add here under schema, I'll add actions. And I'll call this action inc for increment. And an action has a when part and a then part. When should this action happen? Well, that should happen when I have clicked on view counter. And here I point to the named label in my view with this one. Okay, then what should happen? Then what should happen is that I want to increment count. Okay, let's just expand this a bit. Let's try to see if this works. It did, so now it's incrementing. Let's try to decrement. And now it's counting backwards. Okay, let's just try to do the same trick we did with the Codestrates before. So I'll take this one, copy it, open a new tab. And let's try over here, change this back to increment. And then let's go over here and try to hit the button here. And now it increments. So concept state is stored in a configurable data storage. Here, the DOM is used as a data storage. And that is then synchronized through a Webstrate. So the application is multiplayer, both in interaction with it and also in reprogramming it. Let's close this one, full screen this one again. Here we have a very primitive to-do application written in our new programming model. I'll just show that it's interactive, so show some code. I'll do that in a second. Add this to-do, I'll remove this one. So it's interactive. I haven't put the code on the slide, but I can access it from in here. If I can find it, there's a div here, to-do list, and here's the concept definition. There's actually 2 concept definitions. We have a convention of splitting the concrete stuff about event handling on the view out in its own concept definition, and then the abstract stuff that defines the data type and stuff like that in a concrete one. This may or may not be a good convention, but one thing it does show is that these concept definitions, they are merged on runtime, sort of like CSS rules are merged. You can see that there's to-do definition here with some schema, and over here there's also some to-do with some actions, and they are merged on runtime. What this means is that this programming model affords incremental software development. And what do I mean by that? We can, for instance, add a new folder with a definition that introduces an assignee to to-do lists. So I just add a new concept definition and extend the to-do concept with some schema, an assignee that's a string. And then I can see in the debugger that it actually has the assignee on it. Now I create a template for the assignee. And what I do next is that I copy over the to-do template and override it and put in the reference to the assignee template. And immediately it's available in the user interface and can be used. Again, all of this is happening live. Concepts can also be introduced to create domain-specific abstraction layers or effectively domain-specific languages. Here we've created an abstraction layer to create simple board games and implemented Othello on top of it. So here I can play Othello against myself. Let's see if it works. I think I am. 1 second. Let me just reload because I think my computer has again run out of memory. Yeah. Give me just a second. It happens when I'm also live streaming from a 4K display. Okay, I'm back. Now I should be able to play. Yes, I can play Othello against myself. We can take a look at the code and let's open up here again and find the Othello example, board game example, and there's the Othello rules. They're here. Now, you just get a very brief glance of them, but in fact, all the Othello rules are built on top of board game abstractions and sort of written in a domain-specific language for board games. Now, say I want to make a little change so players have 2 turns instead of 1. It can be a bit daunting to edit other people's code, but our hypothesis is that it's easier to make a small extension that overrides or adds some rules. And that's what we can do here. So I've pre-baked a small extension that makes an extension to the game that gives 2 moves instead of 1. So I'll enable this one. And now it's black's turn. So I make a move. And now it's black again. I make a move. Now, well, black 1. Let's just reset the game. Black's turn. And well, let's disable it now because now black will win again. It's white's turn and black's turn. And enable it again. Now it is white's turn and white's turn again. Okay, there you saw it. Okay. So having these programs expressed as data structure also makes tooling quite easy. It's, for instance, easy to create a structured or visual editor. We've made a small prototype of that where, for instance, we have a Blockly-based editor here. What this piece of code shows is the code for a new game. So if I detach this one here, then no, there's no new game happening. But if I attach it again, the game resets. We also have a mapping between our data storage and UI that lends itself well to tool support. So I can right-click with a control right-click here and inspect this in Cauldron, and then I can see the data for this particular concept instance, and I can, for instance, change this to white. And when I hover over these, they show up in the user interface. Okay, soon you should be able to hear much more details about how this is implemented and stuff like that, and also get hands on it yourself, because hopefully, as soon as we get a paper accepted, we will open source the code. Okay. Back to Elise. My goal is to make life a bit better for all the Elises out there, so they can claim control over their software. With future software based on the ideas I showed you, it should be straightforward for her to make a little patch to fix the broken word counts, and for the nonprofit to use the tools they prefer while still collaborating with Elise and the other stakeholders. What I've shown you are just prototypes of ideas, and there's a lot of challenges still ahead in realizing each and every single one of them. But I hope to have shown you that there's a different path than the trodden path of application-based software, and inspire you to explore some alternatives with me. And with that, I want to say thank you, and I open up the floor for questions.
All right, so we're going to do questions both remote and in person. So if you have a question, you can raise your hand or ask in Discord, or if you're in person here, we'll try and pass this mic around. So I'm just give you the mic to start. So, and then if someone raises their hand, you can pass it to them, please. So first,
can you turn on the video for the room?
Yeah, 1 second. First, I want to say, if you were watching Discord, June was trying to connect to your Webstrates live and your slides, but he failed. So good job with that.
I discussed with my grad student Marcel whether anyone would actually do that. Try to do that, but that's nice. Someone did.
Yeah. So I'll kick it off with a question. So you've been building all this stuff on the DOM. You just kind of chose the DOM as your data structure. What kind of frustrations and limitations of the DOM you said, man, I wish we had a better DOM? What do you miss?
As you see that sometimes, with very big web pages, there's some memory limitations, and obviously we are just with the slideshow I showed you. I'm pushing the limits of what fits in the browser memory. So there's some limitations there. One thing that we've struggled with figuring out is how to do something like what we call partial transclusion, so that you can transclude part of a document into another. And we haven't really grokked how to properly do that using the DOM yet. And one thing that I've been inspired of is, I don't know how many of you know of the Dexter reference model for open hypermedia. But I would really like to support the types of hypermedia mechanisms that are described in that. That includes, for instance, partial transclusion and bidirectional links and stuff like that. And there we just hit some of the limitations in the web stack to do some of those things.
Yeah, you just kind of wish you could make your own browser.
Yeah, well, and I think one of the reasons that we've made it so far is that we haven't tried to do that and actually just hacked something together on top of web technology, and then it worked good enough so we could actually start exploring some of the ideas that we wanted to explore.
Okay, we got a question on Discord, and then we got a question in the room, and then a few more, and then a few more in Discord, and then Jens.
Yep.
All right, Josef, do you want to ask your question out loud, or otherwise I can read it?
Yeah, sure. Does it work?
Yep.
Yep.
I hear you.
All right, thanks. So very cool. Thanks for the presentation. Yeah, how do you handle user security? So if you evaluate scripts on the client side and scripts are passed around between users, how do you go about that? Or either intentional bad code or unintentional, such as infinite loops, etc.
Yeah, so actually the first time I ever presented Webstrates, I sent a link to my slides to 30 participants in an online talk. And one of them had an extension that put in an add script in my slides. And this spread to all browsers. And then all browsers just started pumping ads into the slides, and our browsers crashed and it was a mess. So that's definitely a problem. What I do now is I have basic Unix-like permissions on web pages. But obviously, if you have write permissions, this is still a problem. We have something that we call protected mode that is sort of a semi-waterproof method for detecting if it's actually our code or it's an extension or it's a library that puts stuff into the DOM, and then it won't persist it if it isn't our verified code that does it. And that works for 99% of the cases, but it's still an unsolved problem, I must say.
You had a question? We got a question in the room now. It should be on, but oh no, hold the button if it's not, if you don't hear it. No, can you hold the button?
Okay, how about now?
There you go.
Oh, okay, good. So neat talk, thank you. I'm wondering, usually synchronization is really tricky, and you seem to use synchronization a lot. I was wondering if you could talk a little bit about kind of how you manage that, technical challenges, safety, consistency. How do you do that?
Yeah, so basically what made this possible to begin with was that one of the engineers on Google Wave open sourced the implementation of operational transformation in a library called Share.js. And Share.js was one of the first open source libraries that enabled synchronization of JSON, arbitrary JSON. And what I did was basically take that library and then map it to a JSON representation of the DOM in something called JSON ML. So behind the scenes, I have a JSON representation of the DOM that I synchronize and then map to the DOM in the browser. And that works fairly well. There's a lot of edge cases in the DOM that we have spent years on figuring out how to solve. And it's also relatively naive. We don't support moving trees around, so we only support deleting and adding. And sometimes it can break. But now Jonathan Edwards has asked, have you thought about version control for our Webstrates? All of these problems we typically handle by rolling back to a previous version where it hasn't broken. But for everyday use, we never experience synchronization issues. It's mostly when someone does something that programmatically manipulates the DOM very fast or something like that, where things might break. But I'm very interested in porting Webstrates to CRDTs and making it decentralized, but that's a topic for another talk.
Thank you.
Camille's wondering about forking a Webstrate so that you can make a copy or something that doesn't refer to the previous one, and it's how do you handle that so that you
so partly to also answer Jonathan's question in full, we have full versioning of Webstrates because of operational transformation that has a full log of the operation, so we can just roll back to a previous version, and we can name those versions with tags. It's relatively easy to just copy a Webstrate, and so we have this prototype-based copying. You can put a question mark copy after a Webstrate, and then you create a copy with it. It's much more difficult to merge them back together. And here we've been mostly using the Webstrates package manager to bundle code as these packages that we then easily can move between Webstrates, so basically making a parallel versioning structure for our code on top of it. Let me see what testing a new feature for game without breaking other schemes. Yeah, but that would typically just be by making a copy and then moving over the code either manually or through our package management system.
All right, thanks. Jens?
Yeah, thank you. I was wondering, maybe it applies to Codestrates or Webstrates or the unnamed project in the same sense. How do you deal with when dynamical content, so when some part of code or generates new parts of the web page, like the ad did in the first example, and sometimes maybe as a user you would want to say, okay, now I generated some content, some div, and I want to continue, and it becomes maybe static, and I want to customize it. And sometimes it's, oh no, this is just dynamic data, I have to throw it away, and there is a static part that forms the application. So how do you deal on a web page? There's dynamical and more statical elements, but
right.
The user cannot distinguish, I guess, so much as a developer can, where to put the right changes.
Yeah. That is well, I wouldn't say fundamental problem, but an issue that we've been working with throughout the whole process. And we've introduced the notion of transient elements. So you can create a transient subtree in the DOM that's ignored by the Webstrates server. So for instance, you can make a toolbar and stuff like that. That's not synchronized also, so you can build what's in groupware terminology is called relaxed, what you see is what I see user interfaces. But still, it's difficult for the users to comprehend the difference between what's permanent in stored on the server and what's transient. And we've been toying a bit back and forth with this. One of the biggest issue was in the first Codestrates to understand that why is it I can edit code and CSS together, but I can't collaboratively edit HTML. That's, for instance, because HTML isn't actually a first-class citizen in the DOM, because the DOM is the DOM. So if you want to edit that, you have to serialize it into HTML and in a parallel way, synchronize it. And there are all these sorts of issues around that. And I think we have made a lot of pragmatic choices to work around that, but we don't have a nice conceptual, clear way of dealing with it.
Thank you.
All right, Mariano on Discord asks, if you had a magic wand, what would be the best substrate instead of maybe the DOM?
Yes, that is a good question. I would, getting back to the idea of also partial transclusion, it would be nice if every node in the DOM had its own URL, and documents could just somehow be composed by references to document nodes, and all of this was in a distributed kind of fashion. But I must admit, I don't know. I think my imagination is perhaps a bit limited to well, I'm not sure. I don't know. Perhaps you can, the rest of you can be inspired by my talk to come up with an idea for what a better substrate for Webstrates would be. But definitely on a small scale, then moving away from a centralized approach to a decentralized approach that would allow for instance, also offline editing of Webstrates, which isn't possible currently.
Yeah, I wonder if you can, like, the little hash sign, the little URL fragment after the hash sign or the pound sign.
Yeah.
How well can you index into the page using that? You could use XPath after that or something. I don't know. But that only gives you URLs. It doesn't give you the transclusion bit with iframes that you want. Yeah. Jeffrey, you have a question?
Thanks so much for the inspiring talk, Clemens. It seems like, a lot of your examples, or some of them, required the person doing the modification to have some programming experience in JavaScript. Right. But then later you showed maybe, the block editor. And I'm curious where, non-programmers fit into these projects you've done. And in particular, have you had people with less programming experience try to use them? And what have you learned from that?
We've learned that people with less programming experience can't modify the software that we built. So we're definitely not at a point where end users in the traditional sense the software is not malleable to them. Well, I can just say that there's a long path ahead of us. I think we are moving in a direction with the new programming model that we are experimenting with, where software becomes more composable of ready-made parts, and each part isn't as entangled in complex code with event listeners and difficult software architectural constructs as it typically is. But there's still quite a long way to something that's usable by end users. And just building, for instance, a user interface to do user studies on the new programming model that we've been working on will require that I get some significant funding to build something that is actually usable. And that's also, one of the limitations is that we don't have time and resources to build all the stuff that we would like to build to actually make this end user reprogrammable.
It's almost like you're reinventing the entire stack, or the entire, at least, user-facing stack of editors.
Yeah.
Jess asks, how much time do you spend living in the future and using your own Webstrates on a day-to-day basis? What's that been like experientially?
So I use it quite a lot. I use it for a lot of my presentations, as you see here, and also use it a lot for teaching. So I create notebooks for my students where they can do assignments, and we have here at Aarhus University, we have a teaching server called the Warp that the students use Cauldron to build prototypes where they rapidly can do coding together and build interactive prototypes that are collaborative in ways that are difficult to build by themselves. I would say to begin with, I tried as much as possible to build my own tools for note taking and stuff like that. But I must also admit that with growing responsibility, I got less and less time to build my own tools and started to resort to sometimes using Keynote and sometimes using Evernote and whatnot to keep my notes. But I try as much as possible to use it, and we also use it a lot to build research prototypes for all sorts of projects. We have had research projects running at the local library. We've done prototypes for design studios in the city, and so we use it quite a lot.
Is there one thing that you feel is missing? Like, oh man, I just have to go to Keynote now, or is it just too hard? Is it like too hard to get?
Well, yes. Visual editing of slides. It's empowering to do your slides in CSS, but it's also very, very cumbersome. And sometimes I just want to drag and drop stuff on my slide and position it by hand. And yeah, that I miss.
All right, well, let's thank Clemens for a great talk, and really enjoyed it.
Thank you. Thanks for the questions.
It's great to have you.